In this video, we'll use Excel to explore the tail behavior of a rational function that diverges on both tails. The first question gives us a function f of x, where we have a second-degree polynomial in the numerator and a first-degree polynomial in the denominator. We're asked to use Excel to create an input-output table to identify the tail behavior of the function. I've already created an input-output table for this function. To explore tail behavior, I'm going to insert some rows that allow me to explore the left tail behavior. The left tail behavior will be explored by inputting x values such as x is negative 100, negative 1,000, negative 10,000. The x's are diverging down towards negative infinity, and I identify the y values that exist at those x's. So I input negative 100, negative 1,000, negative 10,000. I drag the y values formula up, and I see the y value is negative 31, then negative 331, then negative 3331. If you think about what this would be looking like on the graph, we're saying as you go to negative 100, then negative 1,000, then way down there to negative 10,000, which would be off my screen. The y value is negative 31, then negative 331, then negative 3,000. Again, that would actually be much lower than that, way off my screen, plunging downward towards negative infinity. So on the left tail, the function f of x diverges towards negative infinity. Now let's explore the function behavior on the right tail. To explore function behavior on the right tail, we need to consider x's like x is 100, x is 1,000, x is 10,000. The x values are diverging upwards towards positive infinity. We drag down the function formula in the y value cells, and we see the y values are 35, then 335, then 3,335. Again, if you think about this on a graph, we'd be saying, all right, at 100, it's a height of 35. At 1,000, it's higher at 335. Again, this is not to scale at all. Way off my screen would be 10,000. Would be much higher. So again, it's actually shooting upwards to positive infinity. So on the right tail, the function is diverging upwards to positive infinity. Before we go on to another example, I want to make note of a general pattern that exists in rational functions. It turns out that in general, we can identify the tail behavior, the end behavior of any rational function by finding the leading term of the numerator and dividing it by the leading term of the denominator. So for example, in the function we were just working with, the function we were working with was f of x equals x squared minus 8 over 3x minus 15. The leading term of the numerator is the x squared. It's the term of highest degree in the numerator. The leading term of the denominator is 3x. It's the term of highest degree in the denominator. So to identify the end behavior of the function f of x, it would be x squared divided by 3x. So notice, one of the x's cancels out, leaving x in the numerator and 3 in the denominator. So it would just be 1/3 x. This is the tail behavior of the function f of x. It will look like the tail behavior of 1/3 x. So what does 1/3 x look like? Well, that's just a straight line that looks like this. On the right tail, it diverges up to infinity. And on the left tail, it diverges down to negative infinity. That is the behavior of the tails of f of x. The tails of f of x will look like the tails of the function y equals 1/3 x. Now let's try a second example. In this example, we've been given the function f of x equals this third degree polynomial divided by the second degree polynomial. We're asked to again use Excel input-output table to identify the left and right tail behavior. So let's first just use that pattern I described a moment ago. We said that if we want to identify the tail behavior, we should divide the leading term of the numerator by the leading term of the denominator, and that should tell us the tail behavior of this function f of x. So x cubed divided by negative 2x squared. Two of those x's cancel out. So that leaves x on top and negative 2 on the bottom. In other words, that is negative 1/2 x. The tail behavior of this rational function f of x will look like the tail behavior of the function negative 1/2 x. What does that function negative 1/2 x looks like? It's a line, so it looks like this. It's a straight line going downward. On the right tail, it diverges to negative infinity. And on the left tail, it shoots up to positive infinity. That is the tail behavior we should expect to see. Now let's just use the input-output table in Excel and make sure that it actually does that. So on the left tail, I'm going to insert rows into the table and explore the behavior on the left tail by inputting x values such as negative 100, negative 1,000, negative 10,000. I drag the y value formula upward, and I see indeed the y values are 46, then 496, then 4,996. They are shooting up towards positive infinity, just like we said they should. The left tail, the function diverges to positive infinity. Let's do the same thing on the right side. To explore function behavior on the right tail, I plug in x values like 100, 1,000, 10,000, and I drag down the function formula, and I see the y values are negative 53, then negative 503, then negative 5,003. They're plunging downward towards negative infinity, just like we said they would on the right tail. So on the right tail, the function f of x does diverge towards negative infinity.